In this video, we're going to be looking at graphing the antiderivative of a function two different ways, and then we're going to look at an application problem. So first, let's look at graphing the antiderivative of a function. So here's a given function. We need to graph the antiderivative of this function on the second graph. Well, what can we determine about the function? Now, over here, this is what we are trying to graph, the antiderivative. And the way I like to think about this is, I like to think about this as the derivative, and this is the function itself. So if I'm looking at this being the derivative of a function, this would be the antiderivative. So I look at the graph and I think, what does the derivative tell me about a function itself? I know that if the derivative is negative, the function itself is decreasing, and if the derivative is positive, the function is increasing. So looking at this graph is negative from about 0 to 0.6, let's say. So I know the function itself is decreasing on this interval. And then from 0.6 to about 2.8, we'll say, we could see that the function itself is increasing. And then from here on, since the derivative is negative, we know the function that we're trying to graph would be decreasing. So there's some information we can use in helping us graph the antiderivative. Now, what else does the derivative graph tell us about the antiderivative? Well, if the derivative of a function equals 0, which it does here and here, we know that if we set the derivative equal to 0, we can then determine critical numbers and we can find any local max or mins. So at this point right here, let's say it's 0.6, since the derivative equals 0 there and it's decreasing before we get to that point, so the function would be decreasing, and then it changes to increasing, we would have a local minimum. So we have a local minimum there. And here's the second place where the derivative equals 0. And the derivative tells us the graph is increasing and then changes to decreasing, so we would have a local maximum at this point. What else can we determine from the derivative? If I have a graph and I look at the derivative of the graph and where it equals 0, which is this point right here, we're referring to the second derivative, because this graph that we're working with here is the derivative of some function. And if I'm looking at the slope of a tangent line, I'm looking at the second derivative. What's happening with the second derivative? Well, at this point, the second derivative equals 0 because the slope of the tangent line at that point is 0. Likewise, down here, the slope of this tangent line equals 0. So f double prime of x, the second derivative, would equal 0 here. We know the second derivative tells us about the concavity of a graph. Now, if we analyzed what's happening with the slope of the tangents from 0.6 to 2, we can see the slope of the tangent lines are positive, but then they change to negative. And we know that if the second derivative changes from positive to negative, we have a point of inflection there, and it's concave upward because the second derivative is positive from 0.6 to 2, concave upward. So it's on this interval here, it's concave upward from 0 to 2, it's concave upward. But then the slope of the tangent lines after 2 are now negative. So it would be concave downward. So it appears that it's concave downward. That's where the slope of the tangent lines would be negative. And then from here on, it looks like the slope of the tangent lines would be positive. So again, we'd be concave upward. So let's try to put that all together and graph the antiderivative. Now we do have an initial condition. It says f of 0 equals 2. So we can plot a point at 0, 2. Now we are decreasing from 0 to about 0.6, and we're concave upward. So here's about 0.6. We're decreasing concave upward, and we can see we have a local minimum at 0.6. So right about there we have a local minimum, and we're concave upward. But now we've changed to increasing. We're increasing from 0.6 to about 2.8. But we do have a point of inflection at 2. So we're going to change our concavity. We're increasing, concave up, but now our concavity changes, but we're still increasing. But now we're going to be concave downward. And right before 3, we have a local maximum. Now we are still concave downward all the way to 4, but we are decreasing now. And we have a, we drew in our, I missed the concavity point here, discussing the concavity. A little after 4.1, let's say 4.1, we have a change in concavity again. So we are decreasing now and concave downward, and a little after 4, we're going to be changing concavity. So let me mark off 4 here. So we have this general shape, but now we're going to be changing concavity. We are still decreasing, but our concavity changes to concave upward, but we're still decreasing concave upward. And we continue to decrease, and we are still concave upward. So that could be a graph of our antiderivative. Now you may be asking, well, how far do we know? We go down here. We could look at the slope of the tangent lines a little bit more accurate to get a little bit more accuracy here, but we're just trying to find a general shape. So if we went down here like this, that would be okay, and so forth. We could go a little bit higher for the local max, but this would be the general shape of our antiderivative. So remember to look at those points on the graph that helped us graph this antiderivative, and let's point those out. Here we said we would have either a local max or min, and we identified this to be a local min on our graph. Here we said we would have a point of inflection since the second derivative would equal 0. So there's our point of inflection on our antiderivative. Here we said we would have another local max or min, and we identified it as a local max. And all the while we're looking at the increase decrease of the function also. We could be talking about that. But here is our local maximum. And again, we would have a point of inflection just after 4. So we drew in our point of inflection there, and we're below the x-axis, so we'd continue to decrease. So those are some relevant pieces of information we can take from this graph to graph the antiderivative. Here's another example. Sketch the graph of the antiderivative for this function, the square root of 1 plus x cubed minus x. And we're given an initial condition. Now we're going to do this one a little bit differently. The last one we were able to graph the antiderivative given a function. We graph the antiderivative from looking at that graph. Here we're given the equation of the graph, and we're going to use that to graph the antiderivative. So our technique is going to be a little bit different here. What we're going to do is draw a directional field. And again, think of this as the derivative of some function. So this is telling us about what the graph is, where the graph is increasing and decreasing. And that's the idea behind a directional field. We're going to look at what is the function doing for different values of x and draw little tangent lines in there to get a feel for the graph of where it's increasing, decreasing, and what's going on with the graph. So let's look at that technique. Let's look at when x is 0. If we plugged 0 into our function, which is representing the derivative of some function, we would say the slope of the tangent line when x is 0 is 1. Because we plug 0 into our function, we'd get the square root of 1 plus 0 minus 0. So the slope of the tangent lines when x equals 1 would be, when x equals 0, the slope of the tangent lines would be 1. So when we go to our graph, which is going to be on the next slide, when we look at our graph, we're going to go to x equals 0, and we're going to draw in little tangent lines with a slope of 1. So anytime x equals 1, the slope of the tangent line, we know the function would be increasing when x equals 0. So we'd draw in those little tangent lines. When x equals 2, if we plug 2 into this function, we'd get 1 plus 2 cubed, which is 1 plus 8 is 9. The square root of 9 is 3. 3 minus 2 is 1. So again, we get a derivative when x equals 2. The slope of the tangent line again is just 1. So all along this vertical line, when x equals 2, slope of the tangent lines would be 1. When x equals 1, if we plugged 1 into the function, we'd have 1 plus 1 cubed, which is the square root of 2, minus 1, which is 0.41. So whenever x equals 1, the slope of the tangent line is going to be 0.41. So it's going to have less of a slope than at 0 and 1. So if we drew those tangent lines in when x equals 1, it would look like this. We could continue on for different values of x. Now if we did x equals 3, we'd have 1 plus 27, the square root of 28 minus 3. You can see the slope of the tangent line when x equals 3 gets very, very steep. Very steep. So the function is increasing very rapidly when x equals 3. If you plugged in x equals 4, you're going to get the square root of 65 minus 4. So out here at 4, the tangent lines are going to be very, very steep. So the function is increasing very rapidly here. So that's the idea behind a directional field. We draw in these slope of the tangent lines for different values of x, and then we can get a feel for what the function is doing. Now we could do the same thing with negative values if the function allows it. This one would. We could plug in -1 for x and get 1 minus 1 is 0 minus a -1 would be 1. So the slope of the tangent line would be 1 when x equals -1. And then we could plug in -2. If we plugged in -2, we would get 1 plus a -8. Now, we would have a problem here because we can't take the square root of a negative number. So those are the values that we could look at the slope of the tangent lines. Now, it does give us an initial condition. So if we started our graph at our initial condition, which is when x equals -1, y equals 0. There's -1, 0. Now, when I draw this graph, I'm going to be parallel to these tangent lines as I pass by them. So I can see the functions increasing like this at -1. But then when we get to 1, we said the slope of the tangent line is 0.41. So it's not quite as steep there. But now as I let x get larger and larger, here being parallel to the tangent lines at x equals 2, the slope again I believe was 1. But now as we go to 3, you can see the graph should be very, very steep. And as we get to 4, the graph is going to be very, very steep there. So this is the graph of the antiderivative using a slope field. And I had to do it on this slide instead of jumping back and forth between a slide. But we could have done it and it would have looked much better if we would have done it on the next slide. But the results would have been the same. We could have graphed the tangent lines, and then we could have graphed the antiderivative using this directional field. So we found slope of the tangent line was 1 here, and we found the slope of the tangent line was 0.41 here. So we would draw the tangent lines in, and back here at -1, it was again 1, I believe, and so on. And at 3, it started to increase. It was very steep here. And we could actually check 2.5 and 1.5 and so on. And then we could draw in the antiderivative using the slope of these tangent lines to see the flow through the graph, what the graph is doing as we go through these values of x. Rectilinear motion. Let's look at a problem involving straight line motion. That's rectilinear motion. Recall that if an object has a position function s equals f of t, then the velocity function is the derivative of that position function. This means the antiderivative of velocity is position. So if we take the velocity function and find the antiderivative of the velocity function, that gives us our position function. Since acceleration is the derivative of velocity, if we take the antiderivative of acceleration, we will get our velocity. So if you have the acceleration function and s of 0 and v of 0, those are initial conditions, take the antiderivative of the acceleration twice to get the position functions. And you can find those constants that we get when we find the antiderivatives. And then we can solve for those since we're given s of 0 and v of 0. Here's an example. A particle moves in a straight line and has acceleration given by a of t equals 6t plus 4. Its initial velocity is v of 0 equals -6, and its initial displacement is s of 0 equals 9. Find the position function s of t. We're given the acceleration a of t equals 6t plus 4. We know to find velocity, we can take the antiderivative of our acceleration. So if we take the antiderivative of our acceleration, we would get 6t squared over 2 plus 4t plus c. So if we clean that up a little bit, we get 3t squared plus 4t plus c. We should be able to solve for c, since we were given an initial condition v of 0 equals -6. So that means when t equals 0, v of t equals -6. So we would have -6 equals 3 times 0 squared plus 4 times 0 plus c. So it gives us c equals -6. This goes to 0, this goes to 0, c equals -6. So our velocity function is 3t squared plus 4t minus 6. We know that the position function comes from the antiderivative of our velocity function. So let's find the antiderivative of our velocity. It would be 3t cubed over 3 plus 4t squared over 2 minus 6t plus some constant. And if we simplify it and clean that up a little bit, we'd have t cubed plus 2t squared minus 6t plus d. Now we were given an initial condition for our position. It says if t equals 0, s of t equals 9. So we would have 9 equals 0 cubed plus 2 times 0 squared minus 6 times 0 plus d. And we see these go to 0. So d equals 9. So we have our position function, s of t equals t cubed plus 2t squared minus 6t plus 9. So that's what the problem is asking us to find, our position function. And there we have it. A ball is thrown upward with a speed of 48 feet per second from the edge of a cliff 432 feet above the ground. Find the height above the ground t seconds later. When does it reach its maximum height? When does it hit the ground? We know that for a free-falling object, if a ball is thrown straight up and it comes straight down, that the acceleration acting upon the ball would be 32 feet per second squared. To find velocity, I'm just going to find the velocity function and position function, because I can see up here, when does it reach its maximum height? I'm going to need the velocity function, set that equal to 0. When does the ball hit the ground? we're going to have to find when the position function equals 0. So we're going to need these functions to answer those questions. So if we find our antiderivative, we'd have negative 32t plus c. Now it gave us an initial condition. It says we're throwing this up at an initial velocity of 48 feet per second. So our velocity at time equals 0 would be 48. So c equals 48. So our velocity function is negative 32t plus 48. To find the position function, we take the antiderivative of our velocity function. So we'd have negative 32t squared divided by 2 plus 48t plus d. And using the initial condition that the cliff is 432 feet above the ground, at time 0, we haven't thrown the ball yet, so at time 0, our height would be 432 feet. And I could have cleaned this up a little bit. Let's do that before we find. So we have this. And now we're going to solve for d. So using this equation, I'm plugging in 432 for its height at time 0. So 16 times 0 squared plus 48 times 0 plus d. So here we see d would equal 432. So we have our position function. Negative 16t squared plus 48t plus 432. And now we can answer our questions. When does it reach its maximum height? Now its maximum height would be found by, and I'm going to call this part A, maximum height would be found by setting the derivative equal to 0, the velocity function. So if we set our velocity function equal to 0, this would give us the time in which the ball reached its maximum height. So we'd subtract 48, divide by negative 32, so that looks like it would be, what is that, 1.5 seconds. And then part B, it asks us to solve when does it hit the ground. Now this would be solved by taking our position function and setting it equal to 0. So we'd have 0 equals negative 16t squared plus 48t plus 432. So we could try to factor this. If it's not factorable, then we would use the quadratic formula, and we would get our value for t. Now this value for t, I do have the actual value listed on the last slide, and I believe it's the exact value is someplace around 3 plus 3 squared to 13 divided by 2. So it's our approximation would be about 6.9 seconds.